Hi, I'm Mr. Mac. We're going to talk about magnetic flux. We represent magnetic field as a series of lines running from the north pole of a magnet to the south pole, as shown in this diagram. If we move a wire or metal conductor through these lines and cut through this magnetic field, an EMF is induced between the ends of the wire. The term EMF stands for electromotive force. It is not a force as such, since it is measured in volts. I call this EMF an oomph, since electrons are oomphed in one direction to give a difference in electric potential. Using the right-hand rule, as the wire moves down, positive particles are forced towards us or out of the page, and negative electrons are forced away from us. The faster the wire is moved downwards, the more EMF is induced. The voltage produced depends on the rate at which the magnetic field is being cut. Magnetic flux is the product of the average magnetic field times the perpendicular area that it penetrates. To make the voltage higher, we can use stronger magnets to give a stronger magnetic field. We could also make a circuit with many wires in a coil instead of simply one wire. This would increase the EMF induced. The EMF is equal to the rate of cutting of the magnetic flux. This is described by Faraday's law, and you need to learn this. It is given by epsilon equals minus n delta phi over delta t, where epsilon is the EMF, n is the number of turns in a coil, and delta phi over delta t gives the rate of change of magnetic flux. So here it is, Faraday's law as a mathematical equation. The little e on the left is the Greek letter epsilon, and it represents the EMF. So EMF equals negative n delta phi on delta t. Try to think of EMF, electromotive force, as an increase in energy gained per unit charge by charges passing through a supply, and it's measured in volts. We can use Faraday's law to define magnetic flux. So a magnetic flux of 1 Weber per second, and notice it's pronounced Weber, not Weber. A magnetic flux of 1 Weber per second is being cut by the wire if 1 volt of EMF is induced. The SI unit of magnetic flux is named after the German physicist and co-inventor of the first electromagnetic telegraph, Wilhelm Eduard Weber. Now we need to understand magnetic flux density. If we have a square of 1 meter that is perpendicular to the magnetic field, so that the lines in our diagram cut through it, then imagine how many arrows would go through it. In this simple diagram, there are 4 arrows in the 1 square meter area. If the total magnetic flux through an area of 1 square meter, which is perpendicular to the field, is 1 Weber, then the magnetic flux density is 1 Weber per square meter. Note that 1 Weber per square meter equals 1 Tesla. That is, 1 Weber is equal to the magnetic flux in a square meter whose flux density is equal to 1 Tesla. It's not hard to see that magnetic flux is a useful tool for helping describe the effects of magnetic force on something occupying a given area. Magnetic flux is the product of the average magnetic field times the perpendicular area that it penetrates. So phi equals BA, as you can see below the diagram, where B is the strength of the magnetic field and A is the area perpendicular to the field. We can now use this formula to calculate the magnetic flux, given the strength of the magnetic field B and the perpendicular A area. I'm Mr. Mac. Thanks for watching.